Welcome to this video about quality of service on the LAN. This is a concrete example of how we deploy quality of service on our own internal office network that might give you some ideas, some pointers of the kind of steps involved in doing this on your own network. So this is the kind of thing we do and the kind of thing we do for our customers. I'm assuming that anybody watching this video already has a kind of CCENT level understanding, so you understand what a VLAN is and why VLANs are used, and you probably already know that you need to have some kind of QoS on your network for some reason, and that's why you're watching the video. First of all, what is QoS? In an ideal world, we'd have enough bandwidth to do everything we want to do all the time. But in the real world, quite often we have applications who have a requirement from the network to have priority access to resources. So general web browsing from the office is not business critical to us, whereas making a high quality telephone call over voice over IP is a critical business need to us. And so all businesses will be able to look at their applications and decide that some Ethernet frames, some packets are more important than others. And in the absence of insufficient bandwidth, you want to be able to prioritize some packets and frames above others. So it seems pretty simple. You just turn on QoS and you sort out your problem. As with all things in life, it's not quite as simple. There are 3 steps to implementing a quality of service policy. The first of all is to identify what traffic it is, which applications you want to treat differently, and deciding what the policy will be. And then you need to be able to classify the traffic. You need to be able to identify which is your special traffic and which is not your special traffic. And then you need to be able to do something differently to those different types of traffic, so applying different queuing behavior. In our case, we have lots of things going on the network, but what we want to ensure that is that our voice over IP frames are guaranteed to get through in the event of congestion at the expense of data. And in our case, we have database applications, SQL applications, file server uploads and downloads, internet email, things going on. So we want to ensure that voice always takes priority over these things. The setup on my desktop and most people's desktop in the office is that their normal day-to-day PC is plugged into the back of an Avaya IP Office telephone handset, and then from the IP Office handset we cable down through Cat5, Cat6 cable under the floors into closets in each wing of the building where we have Ethernet switches. And we also have on our LAN and an Avaya IP Office. In the real world, we have lots of Ethernet switches and lots of telephone handsets and lots of PCs going on. So the setup is slightly more complicated than the slides will suggest. And in addition to all the voice and data PC stuff going on, we have lots of servers. We have database servers, file servers, all kinds of things that are generating and receiving traffic to and from these PCs and to and from the internet. But for the purposes of the presentation, we'll stick to the example where we have one PC and one handset. And the reason we do this kind of thing, where we plug a PC into a handset and then have a single cable coming out of the handset, is quite often to save cabling. In our case, we don't need to save cabling. We've got plenty of cables running under the floor, but we wanted to demonstrate in our own office the kind of things we do for customers. And it's quite a common scenario that customers have more staff than cabling or more desks than they have cabling available. They expand rapidly, and then it's easier and cheaper to do this kind of thing than it is to get more Cat5 cabling and buy more switches with more ports. And also some people regard it as neater, as simply to have a single cable coming out of your desk that plugs into a wall or floor socket, rather than having multiple cables for PCs and telephones. And it works. We can do this because built into these of our telephone handsets is a little Ethernet 2-port switch. It has one port into which you plug your PC, and the other port goes to your network cables under the floor into the Ethernet switch. And over this link we run VLAN trunking 802.1q, and in our particular network we have separate VLANs for voice and data. But even though we have separate VLANs, the actual Ethernet frames are all coming down the same piece of wiring. People sometimes get confused to think that when you split your network up into VLANs, somehow all the frames coming from the separate VLANs are somehow separated, but they all physically at layer 1 go down the same piece of cabling. And so we have Ethernet voice and data frames coming up and down. And the Ethernet switch is simply making a forwarded decision based on the destination MAC address. This is the default behavior for all Ethernet switches. It looks at the destination MAC address, looks at its MAC address table, and simply sends the frame out on the relevant port. Most switches by default will use FIFO, first in, first out. So a frame arrives, it gets processed as it goes. And the switch doesn't care that you've got voice and data and all kinds of other applications. It's just first in, first out, and there's no separation of these frames. All the bandwidth on a given switch port is shared between both the voice and the data frames. So you can end up with a situation where a PC starts off a very large download, and the amount of data frames overwhelms the port switch speed, in which case this will lead to congestion. And if the switch has more frames to send than the port speed allows, then the switch will simply start dropping frames. That's what it has to do. It can't store these frames indefinitely. It'll have a small amount of buffer space, but once that buffer space is filled up, it will start dropping frames. And the switch doesn't care about which frames it drops. In the default situation, it will drop data and voice frames equally. And these large data downloads, obviously people refer to the internet, but most companies tend to have more LAN bandwidth than they do have internet bandwidth, and so it's normally not possible to saturate a single switch port with internet downloads unless you're very lucky and have an extremely high speed connection to the internet. But even then, end-to-end rate limiting tends to prevent large data downloads. But most companies have on their network file servers, SQL servers, all kinds of business applications running locally, and these have, certainly in our case, these have multiple gigabit ports, 10 gigabit ports. So it's quite easy for one of these servers to send more data than an individual switch port to a desktop can cope with. And the same can operate in the other direction. People process data on their PCs, then want to upload it to a server, and so it's possible to saturate a link to want to send more data from the handset device than the switch can cope with, or the handset device can output itself. And the other classic cause of uploads is people getting viruses. It never happens to us, but people have malware on their PCs that causes large amounts of nefarious emails and all kinds of traffic to be uploaded from their PC onto the internet. So there are lots of different ways in which a switch port could be overwhelmed. And a large data upload from one of these telephone handsets might cause that to happen. The people who make these telephone handsets, in our case Avaya, do guarantee when you read the manual that voice frames coming out of them will have priority over data. So the handset manufacturer does guarantee that it will never drop your voice frames if it has too many data. The voice frames will always go through first. It might vary for your particular telephone handset, so you need to go and read the manual to see how the handset manufacturer deals with the priority of voice frames coming out of the handset itself. So the telephone handset is guaranteed to prioritise voice over data in the presence of large data uploads. But we need to do something similar with the switch. So what you have to do is go to the switch manufacturer's manual. In our case, we have Cisco 3750 switches on our network. So you look at the manual, and the manual says, yeah, this switch can support quality of service. And essentially, there are three things we can do on this switch. First of all, we can reserve a certain amount of bandwidth for your voice traffic at all times. It may well be that you don't want to reserve bandwidth all the time, that you want to have that bandwidth available for data traffic when there's not a voice conversation in progress. So that's an option. And on this particular switch, in addition, or instead of, we can prioritize voice frames, or any frames you want to specify as being different, to always go ahead of other frames. So in other words, turn off the FIFO behavior, so frames will not get processed in order of first in, first out. You say, I want these particular frames to be done differently. So back to our three steps of implementing QoS, we need to identify the traffic and decide the policy. So we've decided that we want to ensure that voice has priority over data. And then we need to classify and mark for traffic. So we need to tell the switch somehow which frames are voice and which are data, because by default it's simply looking at the destination MAC address. And there are a couple of ways we can do this, certainly on the Cisco 3750. The first is to set up IP layer 3 access control lists. We know the IP address of the various voice services we have on the network, so we can create an ACL that says that all traffic to these IP addresses is voice traffic. Or what we can do is allow the voice devices themselves to mark traffic and to use QoS markings, so that they will mark the frames to say, hello, I'm a voice packet, hello, I'm a data packet. And there are two ways of marking packets and frames, one at layer 3, the other at layer 2. The current most favoured technique at layer 3 is to use what's known as diffserv markings, DSCP markings, as defined in the RSC 2474. And at layer 2 we have a mechanism called QoS, class of service, and that relies on an IEEE standard called 802.1p, which is closely related to 802.1q, which is the IEEE standard for doing VLAN trunking. And the reason for this is, if you look at the Ethernet frame, when you turn on VLAN trunking 802.1q, you have areas of the frame, the new frame header, that are reserved for VLAN tagging. So in here you stick the VLAN ID that this particular frame belongs to, but it also leaves a few bits left over. The bits that got left over, the 802.1p people came along and said, we'll take 3 of those bits, thank you very much, and we'll use those for class of service markings. So they took those 3 bits and they decided that we're going to insert a number that gives a priority to a particular Ethernet frame. And this is the suggested scheme that they came up with, where most of your traffic is regarded as best efforts, so that's given a priority 1, or known as BE, best efforts traffic. And if you're running voice on the network, they suggest that you mark those frames with priority number 5 for voice traffic. And the only thing that takes priority over voice traffic will be inter-networking control, so you can maintain your network. At the IP layer, we have 6 bits in the DSCP, in the IP header. We have 6 bits that are used for that were the TOS byte and now used for DSCP. So we have 6 bits to play with, so far more values. And the RSC recommends that these are the kind of values you might want to set for prioritizing your traffic differently. So we have a decimal value 46 in DSCP marking, which identifies traffic to be expedited. In other words, this is priority traffic. So what we're going to do is to mark IP packets with expedited forwarded decimal value 46. Now, both of these tables are suggested values, and you can choose whatever values you want on your network. I would suggest that that's possibly not a good idea, because if you have engineers that come along after you, it's a good idea if everyone tries to follow a standard, so that people come in looking at your network long after you've gone and configured it can at least understand what you're trying to achieve by sticking to standard values. But you can choose whatever values you want. And you can choose on your network whether you're going to use these COS markings or these DSCP markings, or you're going to use neither, or you're going to use both. Now in our case we have to use both, because when you look at the Avaya handset manual, what it wants to do is to set class of service layer 2 markings for frames coming out of the handset. By default, bless them, Avaya mark voice frames coming out of their handset with priority marking number 6. So we're going to change that to priority marking number 5. So we configure our handsets to stick to the recommended value of priority number 5. But be aware that the default for Avaya is 6, and the default for different manufacturers' handsets will be different. So again, you have to go and dig out the manufacturer's technical specification, or look through the interface to see how the manufacturer is going to mark those packets. The IP Office unit itself, the IP500, is going to mark VoIP packets at layer 3 with DSCP markings 46. So at least on that device they're going to stick to the standard. So we've got two things going on. Voice IP packets are getting marked with DSCP 46, and voice Ethernet frames coming out of the handset are going to get marked with COS priority 5. So we're using a mix of both COS markings and DSCP markings. So we now have a way of knowing which frames are voice, and we need to make sure that the voice always gets through, and these are known as PHPs, per hop behaviors. So now we have to configure devices to say, okay, this is a voice frame, treat it differently to a data frame. And again, this is all vendor specific, so what you have to do is go back to your manual. On our network we have Cisco 3750 switches. So we read the manual and we learn that by default QoS is turned off. So when you purchase the switch, it might well say on the side of the box, this is a device that supports QoS, but it doesn't necessarily mean it's going to be turned on as soon as you take it out of the box. So QoS is disabled by default. And when we enable QoS, the way QoS works on 3750 and some other Cisco switches is it creates 4 egress queues per interface. Now again, this will be vendor specific, so you have to understand from your switch vendor's manual what it's going to do. So turning on QoS is really easy on a Cisco. You go to this iOS prompt and you type in MLS QoS, and what that does is create your 4 queues for you per port. So each port now has 4 queues. And because we're using both COS and QoS, the next thing we need to check is that the COS markings are going to be mapped to DSCP markings. So entering the iOS command show MLS QoS maps COS to DSCP shows the mapping between your COS markings and your DSCP markings. So the top table is showing you that COS marking 5 is mapped to DSCP 46. And this is a problem for us because we actually want COS marking 5 to be mapped to DSCP 46 rather than 40, so we're going to have to change that. If you want to see it the other way around, the markings from DSCP to COS, you get the slightly larger table shown below, and you read across from row to column 4 and then down to 6. You see that is correct. So going the other way from DSCP to COS, DSCP value 46 is marked to COS5. So we have to go in and look at the IS command to correct that. So we do that, we correct it. And so now we have COS marking 5 is mapped to DSCP 46. So this is, without going into the details how you do it, again you can Google for the actual commands you need to do, or look it up in the manufacturer. But it's not as simple as simply turning on CORS. You have to look at the detail of what is happening underneath and configure these things appropriate for your environment. So what we end up with is these mappings where COS marking 5, our layer 2 marking, is mapped to IP layer 3 46, which is expedited forwarding, and that's what we're going to use for our voice traffic. Everything else by default is going to have COS marking 0 and DSCP marking 0, which is the default. Now we said these markings are coming from the IP office equipment itself, the handsets and the IP500 unit. And on our particular network we have security mechanisms in place that stop people just being able to plug any old device into our LAN. And so we're pretty confident that anybody who plugs a device into the LAN knows what they're doing. And so we're quite happy to trust that any of these markings coming from a device on our LAN has been configured correctly. Because what you can do, of course, is decide if a company says that you're going to prioritize traffic with DSCP 46 in the IP packet, I can decide to set my PC up to go and mark all my traffic coming out my PC with DSCP 46. So I'm going to get priority over the network at the expense of everybody else. So if you have that kind of environment where you can't trust people and the devices that get plugged in, you probably want to wipe off any COS or DSCP markings you receive first and then re-establish them on your switches. But in our case, to make life easier for us, we're going to trust the markings that come off these devices. So an additional configuration step per port on the Cisco 3750 is to say that we're going to trust the COS markings, and we're going to trust the DSCP markings. Now, by default, when you turn on MLS COS on the 3750, it creates these 4 queues, and it will service these 4 queues based on the shaped round robin algorithm. So it will go to all of the 4 queues in turns, and it will take frames out of the 4 queues equally. You can change that behavior, tweak it, but that is the default. But what we want to do is to have one queue as the priority queue into which we'll stick our voice frames, and 3750 Q1 can be set as the priority queue. That's not the default, so you have to turn it on. And Cisco, the manual says that if you have a priority queue, that queue will always be emptied of its frames first. So the SRR algorithm will go around all 4 queues and start taking frames from each, but it'll keep going back and checking queue number 1 to make sure before it services any other queue that there's nothing left in queue number 1, and it will service queue 1 to absolute exhaustion. So any frames you put in there will have absolute priority over the other 3 queues. And the switch also offers policing, which we don't use, but again you can. This is where you set particular data rates, and you can do that if you want to. Again, if that suits your particular environment. We've chosen not to on our network. And so you have to map your DSCP markings and your COS markings to these particular queues. Without going into the details of how it's configured, these are the show commands. Again, you can simply Google for these things, and it shows us that frames with COS marking 5 are being put into queue number 1, and if you look, you'll see that no other frames with different COS markings are in queue number 1. So queue number 1 is reserved simply for any frames with COS marking 5. And the DSCP markings, you'll see that frames marked with 40 all the way up to 47 are put into priority queue number 1. And you'll see that the default traffic, so call 0, gets put into queue number 4, and you'll see that DSCP 0, unmarked traffic, also gets put into queue number 4. So we end up with a situation once you enable priority queue at, that all the voice frames now go into queue number 1, and everything else ends up in queue number 4. Now these queues are taken from the port buffers. In order to cope with bursts of traffic coming into a switch or a router, all these devices have a certain amount of memory, high-speed memory set aside, where it puts in frames that it's yet to service, that it's yet to send out on a port. And so when you enable QoS and you enable these 4 queues, the amount of buffer space that's allocated to a particular port gets chopped up into 4 different lots. So you take the total buffer space, the common pool of buffers that are available, and it's split up into 4 different queues. And there are various algorithms that you can change to allow different memory, different allocations of buffer to be set on these different queues. Because one of the issues you might find with QoS is that if all your data traffic is now going into Q4, you might find that you don't have enough buffers into Q4. Everything's alright for your voice, but now you're dropping data frames needlessly that you weren't dropping previously, because previously the port just had a large amount of buffer space. Now if you're going to force all your data frames to go into a smaller amount of buffer space, you might start dropping that. So you might find after you've enabled QoS that you might need to do a bit of what's referred to as buffer tuning, which is an art in itself. Rather than a science, you have to start looking at the queues and trying to allocate different amounts of buffer space to these queues to fit your particular traffic environment. Or what you might have to do is rather than saying just having one blob of data traffic, I'm going to start splitting my data traffic up and assigning different QoS values and DSCP and sticking those into different queues. So you end up with a relatively sophisticated custom queue policy. So all these things are available certainly on the Cisco 3750 and other Cisco switches. Different manufacturers will have different schemes. So in summary, voice and data are identified by using QoS markings, QoS markings 802.1p on the frame. The switch enables 4 queues, and one of those queues is made a priority queue, which is always service first. And all the voice frames we stick into that priority queue. So that guarantees that our voice traffic will always leave the switch first in the presence of data traffic. And the handset itself, Avaya TELUS, prioritizes voice frames out. So we've achieved our aim of both the handset now prioritizing voice frames and the switch prioritizing voice frames. In summary, hopefully if you've learnt nothing else, you've learnt that there's no one thing in QoS, and simply turning QoS on is not by itself normally going to do anything for you. The steps that you need to configure QoS on a LAN are slightly more complex, and you have to go digging around, working out what your policy is going to be, and then looking the vendors' particular manuals for what they're capable of. I hope you found this useful. Please leave any comments if you have or you haven't, if you think we can improve it in any way. Thank you very much for your time.